Hello, my name is Adele and I'm with Proximion. I welcome you to Stockholm, the capital of Sweden. Stockholm has a high concentration of companies working in the optical communication field, and Proximion's specialty is dispersion compensation. I hope all of you are going to enjoy the following presentation. Lowering the cost of optical transport is a top priority for both system vendors and network operators. The constant challenge to push costs lower is driven by the competitive nature of the industry, but has in recent years been receiving increased attention in order to justify the ongoing 10G to 40G transition. FBG-based dispersion management can facilitate these needed cost savings by supporting new low-cost amplification strategies and new optimized amplifier designs. The most obvious advantage of FBG-based DCMs is the low insertion loss. Typically, a 120 km FBG DCM has an insertion loss of around 3 dB, while an equivalent DCF has an insertion loss of approximately 10 dB or even higher. Furthermore, the DCM has an advantage in having virtually constant insertion loss versus span length, whereas the loss of a DCF grows linearly with the span length. Apart from the favorable form factor, this also yields another key advantage, namely low latency. The latency or time delay of an optical signal is directly proportional to the optical path length. Latency numbers in the range of 100 microseconds are not uncommon for DCFs, whereas the latency of an FBG DCM is typically 3 orders of magnitude smaller and basically can be considered marginal. Another prominent characteristic separating the FBG DCMs from DCFs is the ability to tolerate high optical powers without suffering nonlinear penalties. A DCF will suffer these even at rather low optical powers, typically minus 2 dBm per channel, while the FBG DCM will not introduce such effects, even at the highest power levels present throughout any traditional optical network. The favorable performances regarding insertion loss, latency, and the lack of nonlinear effects at high optical power, in combination with a significantly smaller form factor, are all key properties, not only allowing for cost-efficient amplifier solutions, but of course also providing substantial cost savings in general. Erbium-doped fiber amplifier designs will benefit from improvements of noise figure, size, cost and robustness. A traditional mid-stage access amplifier, an MSA, is typically designed for mid-stage DCF loss of about 10 dB. This will support approximately 100 to 120 km DCF span length. The same loss budget would allow an FBG DCM a span length of more than 400 km. And since this includes circulators, this also facilitates the exclusion of the loss-prone optical isolators in the amplifier mid-stage block.
The low insertion loss of the FBG DCM may be valued differently depending on network topology, but the low insertion loss can be used to replace the MSA altogether. In the latter case, the direct cost savings on amplification would amount to approximately 40% per span.
A traditional MSA is designed to mitigate the high insertion loss of a DCF by utilizing a dual-stage preamplifier in combination with a booster. Due to the virtual span length independence of the FBG DCM, the two VOAs could be combined into one, leading to a much simplified design without reducing the gain of the preamplifier. Combined with the low loss of the FBG DCM, you can typically increase the noise figure performance with about 1.5 dB. The lower pump power requirement, together with the marginal latency, makes a single optical pump approach possible, thus removing the need for separate independent pumps and control loops for each stage. Taking into account all of the above, we get an MSA design optimized for FBG-based dispersion management. This design has the advantage of much reduced component count, as well as being significantly simplified. This results in up to 30% cost reduction, as well as a 50% footprint reduction compared to the conventional MSA designs. Even further cost reduction can be achieved by integrating the circulator from the FBG DCM within the amplifier. The reduction in footprint can also be translated into significant system cost savings by integrating more components on a single line card. For example, the MSA and FBG DCM may be integrated on the same line card, or two amplifiers can be integrated in the same package and mounted on a single line card. This can be particularly useful in ROADM systems requiring east-west separation of amplifier stages. By utilizing FBG-based dispersion compensation, there are a number of ways to facilitate cost-effective optical transport, apart from the previous example. The specific cost savings that can be achieved are closely related to the specific topology of a certain optical transport link, but some simple and straightforward examples immediately stand out. Drawing on the low insertion loss, the equivalent of hundreds of kilometers of SMF dispersion compensation can be concentrated in single nodes, hence providing cost-effective point-to-point networks. The low loss and high power tolerance further provide the network designer with the possibility of placing the compensation either directly after the mux on the transmitter side or after the booster. In the case of DCF, issues normally arise either from high loss limiting the amount of dispersion compensation close to the transmitter or the introduction of high nonlinearity penalties if placed directly after the booster. As mentioned before, the elimination of mid-stage amplifiers is, in some networks, an attractive strategy to pursue. If such a strategy is fully implemented in a network, the amplifier-related cost saving per span can be as high as 40%. Even in networks where MSAs are not used, the insertion loss-related cost saving could still be significant. By simply utilizing amplifiers with less available output power, the saving on amplification can be in the area of 20% for a standard 80 km span. FBG-based dispersion management provides the telecommunication industry with unparalleled possibilities when it comes to cost and performance network optimization. The increased focus on cost, especially considering the future of 40G and 100G networks, is effectively addressed by this unique and in many aspects disruptive technology, a conclusion supported by the to date thousands of units deployed in various networks worldwide. Thank you for your attention, and if you need any more information, please look us up on www.proximion.com.